Good morning, Regional. Hey, it is Thursday, November 5th. Does that sound right? I'm not sure. Um, and so we're going to talk a little bit about how electrons move. Now, yesterday we did the Hog Hilton, and I know some of you guys worked through it and you did it and you completed it. You moved the little piggies around on the Jamboard. You click, turned it in, and then you're like, I'm not sure what that has to do with chemistry. Um, Again, it's a metaphor, and I'll explain it tomorrow. Okay. There's one more concept that I need to get to you so we can take the Hog Hotel concept idea and what we're going to learn today and put those together tomorrow and try to tie it all together. So today we're going to learn about something called quantum mechanics. Ooh, it's a big fancy word. You want to impress your mom or dad at dinner, say, Mother, we learned about quantum mechanics today in chemistry. She'll be like, whoa. Okay. Now, really what that means, the component of it, the aspect that we're looking at is how do electrons move? Okay, so that's what we're going to be looking at today. How do electrons move? Okay, so we've talked about what are electrons, where are electrons, but how do they actually move? How does that work? Okay, so first of all, electrons travel. They do move, know that, okay? And they actually travel in waves. They are full of energy, and that's why electrons are found on energy levels, right? We've learned about the different levels around the nucleus of the atom, but they don't work in perfect circles. They actually travel in waves. So they move around the nucleus, and they do so in a fixed radius. But here's the deal: electrons are negatively charged, right? The nucleus of the atom, so here we're looking at the nucleus, that's positively charged. Electrons are negatively charged. And by nature, opposites attract. So it would make sense that the electron and the proton would slowly move towards each other until they combine. But the energy itself around of the movement of that electron keeps it from coming and imploding upon itself with the nucleus. Okay, so you'll see here, you would think they would kind of do this and slowly get closer and closer and closer. That doesn't happen. That's not allowed. What does happen is it stays in a fixed radius around the nucleus. But again, it's not circular. It actually moves in a wave. Okay. Oop, what happened? Oops. Okay. Now, the picture you see here is what we've used to represent atoms, and we've called this, remember, the Bohr model. And Niels Bohr is the one who decided and figured out, rather, that there are these different orbitals, and that on different orbitals it holds different number of electrons. So the first inner ring can hold 2 electrons, the next one can hold 8, the next one can hold 16 and 32, right? And we've drawn it, we've built models, and we've made it look like this. But the reality is that's not really how it looks. It's a nice way. We like to do that because we can draw it and we can show it. It's a representation of it, but it's not really how it looks. It's like when my kindergarten does art and he draws a picture of daddy. It's like there's daddy, and daddy has a head and he has arms sometimes and a body and legs, but no one would look at that and say, wow, that's Mr. Geisler. Look, it's like, so this is like the cartoony version, my kindergartner's drawing version of electrons and the energy levels. Okay. Um, and the reason why is because they travel in waves. Right now, they do travel again. Remember, we said they travel at a fixed radius. Remember that? But they move in waves. So this is actually more realistic of what it would look like. This is a hydrogen atom. Okay, and you can see the movement is wavy, but that would be really hard to draw. And the problem with this picture is it's only two-dimensional. It has height and it has width, but it has no depth. So the reality is the way I want you to think of that Think of it like a fan. Oops, what did I do? Think of it as a fan. If you've ever looked at a fan, right, you can see the blades. And the blades are spinning. You can see the picture down there. They're spinning, they're spinning, they're spinning. And if I were to say, okay, where are the fans? You'd say, well, they're everywhere. Look at, I can see them everywhere. But they're kind of nowhere. Oh, what? Like they're moving, so you can see they're there. But if I could freeze time and just push pause, see if I can do it. Okay, now I can see them. Right? I can see the blades are right here. Right? They're not in the lighter areas. But we can't freeze time. All right? So electrons kind of work the same way. You can't say the electrons are right there. You can only predict where they are at any given moment. And this is called the Heisenberg uncertainty principle. Guess who figured this out? Dr. Heisenberg. He said you can't be certain of exactly where the electrons are, only make a prediction of where you think they're probably going to be. So let me show you a picture. Instead of looking at the fan, look at this. Okay? This is how we've come up with the idea of this thing called electron clouds. Okay? And on the bottom, we have what are called density maps. So in the middle, these are both probably hydrogen atoms. And in the middle is the nucleus. You can see it's labeled here. And the little blue dots make predictions where the electrons are going to be found 90% of the time. Right? So where are they right now? I don't know. How about now? How about now? Now. We don't know. It's like the fan. I could freeze time and show you. But I know they're going to move within this area, and that's the little blue dots. So if you could do that and then draw a boundary line around it, that would be what's called a probability cloud. Now we call that an orbital. That's the boundary within which the electron is most likely to be 90% of the time. So we will say the word orbital, and I'll probably do this, saying it's an orbital because it is revolving around the nucleus, but it's not a circular ring. It's more like, think of a cloud. Clouds move, but they kind of wisp and move, and they're unpredictable, and you don't know where they're going to be. That's how electrons move too. That's how orbitals, electron orbitals, work. All right. Now, the dots on the left side represent what's called an s orbital. And if you were to look at that, there's 3 dimensions. That's why the x and the y and the z, they're trying to show it's 3-dimensional. And the shape of that is a sphere, right? It looks like a ball, little teal ball there. And this is called the s orbital. S orbitals are when an electron orbits around a nucleus in an orbital spherical fashion. Okay? But they don't all move like that. The quantum mechanical model of the atom talks about electron energy, and it's limited to quantized values based on the wavelength that will fit around the nucleus. Huh? Okay? In other words, there's different wavelengths which cause different levels. And we can only make predictions about where the electron is likely to be 90% of the time. We call them orbitals. Now, orbitals have what we call our subshells. We have subshell 1, subshell 2, subshell 3, subshell 4. It's kind of like airplanes flying. We've talked about that before. If all the planes fly at the same level, there's more likely of collisions. But if we can put them at different levels, it allows them to move and fly, and electrons work the same way. And this is that quantum mechanical model. Okay, so look at hydrogen, for example. Hydrogen can have multiple different orbitals. It can have what's called a s sublevel. They're spherical. okay? And their size increases based on the quantum number. So if they're number 1, they're little and small. If they're number 2, they're bigger. If they're number 3, they're bigger yet. But s orbitals are all round and spherical. It's a nice, easy way to remember that. S is spherical, okay? Sometimes orbitals can be this shape, and we call these dumbbell shape, all right? And these dumbbells can orient around the 3 different dimensions. They can go across, they can go up and down, they can go front and back. Okay, so s orbitals tend to be round. P sublevel orbitals tend to be dumbbell shaped. Another shape you can have is D. These are kind of, I would call these like clover shape. All right, and there's actually 5 different d orbitals. And you can see them. Now, the one in the middle is kind of a strange looking one. That one's a different, unique one. It's called the DZ2 orbital. It has its own unique shape. The other 4 are like clovers. These are your d orbitals. And then the last one are the Fs, and Fs are funky. F for funky. Okay, and there's actually 7 different F orbitals. And so I want you to think of these shapes. These are the patterns, these are the paths that the electrons can travel. They're not just woo, woo, woo. Okay, they could be dumbbell shape, woo, woo, woo. They could be clover shape. They could be the funky shape. Woo, 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 woo. Okay, look at this one here with the double ring, the double teardrop. Strange, okay, but this is the shape that the different electrons can travel. Now, when you put them all together, they might look something like that. Isn't that cool? So the different colors show the different electron orbitals, and it shows it in all 3 dimensions. Okay, so they kind of intertwine, and it's like a ballet where they're all working together and in sync with each other, but they're not running into each other. They're overlapping but not colliding. Okay. Now I like this picture. This actually shows some of the different orbital shapes and where you might find them. Okay. So this kind of looks a lot like our periodic table, doesn't it? Look at the top left. Top left shows the different orbitals. So in the left 2 vertical groups, those are going to be S-shaped orbitals. Huh. The valley down in the middle, these are our D-shaped orbitals. The mountain on the right side, right? Those are going to be my P-shaped orbitals. And the block in the bottom, remember we called that the F block? Well, this is why. These ones have F-shaped orbitals. So where they lay in the periodic table helps us figure out, well, which shape orbitals do these ones have? Okay. So going back to this, I showed you this slide a few times before. That first sublevel is always an S. The second one, you're going to have the S's, but now you can include the P. The third one, I'm going to have S's, I'm going to have P's, I'm going to include the D's. The fourth one is S, P, D, and the last one can be F. So they build upon each other. As I move out, I get more complicated sublevels, more complicated orbitals. All right, and these are actual pictures. This is from an electron microscope, actual pictures of some different probability clouds of the orbitals, of the electrons moving. And I don't want to get into how they're able to do that, but they're able to do this with what's called X-ray diffraction and showing how the electrons could potentially move. Now, where are they? I don't know. It's like a fan, right? It looks blurry. I don't know where they're at, but I have an idea of where they're at 90% of the time. Okay? And so I want you to see that and know that so that we understand that 1, electrons move, and 2, they move within certain probability clouds. We can identify where they are different 90% of the time, and that they have different shapes. There's spherical, that's the S. There's dumbbell, that's the P. There's clover, that's the D. And then there's the funky shape, that's the F. And those are your 4 different orbitals. All right. So, guys, fill in that note sheet. Hopefully, that's done and taken care of. That's all I have for you today. When you're done with that, click turn it in and you're done. Now, tomorrow, we're going to piece this orbital thing together and the clouds and the different orbitals and tie that in with the Hog Hotel, the Hog Hilton, and try to make sense of those two concepts. It's a lot, but I think if we can do those separately and then try to bring them together, hopefully it'll help turn that light bulb in your mind. Okay? Awesome. Good job. Appreciate it. That's all I got. Peace, guys.